I got my first programming job while I was still in high school, and it was writing C++ code for a Xenix system connected to a Xerox high-speed laser printer. That was 1992. By the turn of the millennium, I was working for tech startups, and I was programming in languages like PHP and Java and deploying everything on Linux and virtual machines. And that's where I first started collaborating in the open source community. Since then, I've expanded my experience to be a contributor to projects like Apache Camel, Eclipse Vert.x, Quarkus, and many other open source projects. Now, after 30 years of experience in the industry, I still learn tons of new things almost every day, and I hope you do as well because it's my favorite part of this job. Today, we're going to have a discussion about how you might leverage a tool like Eclipse Vert.x to build resilient, reactive, scalable, and manageable IoT solutions on top of Kubernetes. My name is Deven Phillips, and I'm a senior architect with Red Hat's Cloud Native Runtimes practice, where we leverage techniques like domain-driven design, design thinking, and contract-first API development to help our customers build more effective solutions with better outcomes. So let's dive right in. The real question we want to ask is, how might we simplify IoT? As I was doing my research to prepare for this talk, I read a number of articles explaining common challenges with implementing IoT. And two things really stand out to me based on my experience and what I've read. One, the volume of data being collected in IoT and industrial IoT systems is just mind-boggling. And two, the challenge of managing that data collection across numerous environments in a cost-effective way is just something that is difficult to even comprehend. Because when you get down to it, IoT in the cloud is expensive. In many of the articles that I've read, they've done surveys with CTOs and CIOs, and they estimate that 80 to 90% of organizations are regularly exceeding their cloud spending budgets. At the same time, more and more organizations are moving to the cloud, which means that hiring mature and experienced people to enable those moves gets harder every day. This in turn makes it even harder for those organizations to align their cloud spend to activities which effectively generate revenue. So every day you're having a more and more difficult time achieving your cloud migration goals. Kubernetes helps. Kubernetes extracts away a lot of the complexity of moving to the cloud by providing a consistent set of practices for doing things like auto-scaling, configuration, management across all your environments. But Kubernetes in and of itself is not the full answer to the challenges of large-scale IoT or large-scale IT in general. What we really need is some sort of hierarchy, a way that we could perhaps aggregate and compress data at the edge. And what if we could compact and stream the data more cost effectively to where compute is the cheapest? And then what if we could reduce memory and CPU consumption at both ends of that equation? Well, what I'd like to suggest to you is maybe trying an architecture similar to what I'm showing you here. This is not unusual for what you might think of in IoT. You've got edge nodes, you've got worker nodes in your head office or in your public cloud environment. You've got Kubernetes masters managing those worker nodes both locally and out to the edge. This can be an extremely good way to leverage the single pane of glass of those Kubernetes masters to manage all the way out to your edge environments. But also imagine those workers are aggregating and compressing that data so that you can stream it up to where you can really effectively process it. This is where Vert.x can really come in nicely. These little tiny Vert.x processes, these container images running on your edge workers, can ingest data over MQTT, WebSockets, TCP, UDP, and they can distributedly process it. Vert.x supports clustering at a very low level. And these instances of these Vert.x applications scale dynamically based on usage and demand. What's really nice about this is these little Vert.x processes can be their own MQTT server or their own WebSocket server with very, very little overhead. And then back at your head office or in your cloud environment, Vert.x can be used to effectively aggregate your data further, customize or structure your data so that it's easier to process. All scalable, again, using small services which scale independently. Something you might notice is in none of this have I shown using things like Kafka or an MQTT server or a database. All of that is for later processing where it becomes more cost effective. What we really need to do is take this large pool of incoming streaming data, aggregate it, and give it structure so that we can more effectively process it in those more expensive systems. These Vert.x processes are absolutely tiny. The JVM version of these running in a container is less than 500 megabytes for the container size. If you compile using GraalVM and native image, that can get down to 20 or 30 megabytes of container size, which is helpful, but not the biggest deal because the size of the container image isn't really that big of an issue. What really matters is that they have extremely low memory overhead and they have very fast startup times so that you can scale up and down so that you're not using resources when they're not necessary. And moreover, these Vert.x applications are extremely performant. They use effective threading by using an actor model and an event bus across a clustered configuration so that the workload can be distributed across as many pods or nodes as you need. This means that you can get full advantage of your multi-core CPUs and efficiently process large-scale binary data. Now, that's the end of the slides. That's really what I wanted to talk to you about, but let's actually see it in an environment. So what I'm going to do is I'm going to come over here and show you that we've deployed a Vert.x application into a Kubernetes cluster. And in this case, this Vert.x application is made up of 3 replica pods. The first thing I want to show you is how quickly I can spin up new pods to address demand. So I'm going to adjust my Helm chart here to increase to 5 replicas. And then I'm going to do a Helm upgrade on my deployment. And you'll see here in just a few seconds how quickly the pods get started and how quickly they become available. So we have a liveness check that checks every 2 seconds to ensure that the applications are up. And you can see our first pod is up, and now our second pod will be up momentarily. That's pretty quick scaling for a Java-based application. Now, if I had compiled this application to a native image, the startup would have been measured in milliseconds. Additionally, if we dig into these resources, let's look at one of these Vert.x pods and take a look at the metrics. Oh, that's the new pod, so of course it doesn't have any metrics yet. Let's go into this one. This one has metrics. Something you'll notice is that memory utilization on this pod is only 250 megabytes. Most of that is Java Virtual Machine overhead. And then the CPU utilization is only 5% of one CPU, even while it's doing its work. Now, what does this application do? Well, not a whole lot, because it's a relatively simple proof of concept. What it does is it provides a web server that presents this particular web application. This is a Vue.js web application. This application is a hybrid mobile desktop app, and it communicates back to the Vert.x application over both MQTT and WebSockets. So MQTT to stream sensor data. So for example, if you were to load this application up on your mobile device, and I'll show you a link for that momentarily, you could see the device motion sensors streaming data back to my Vert.x IoT application. And you would see live data streaming right there inside of your web console. Now, the WebSocket communication is coming back from the Vert.x application, and it's displaying this aggregate. So every time I click on the desktop app, it streams the X and Y coordinates over MQTT to the backing Vert.x application. And the Vert.x application, every 2 seconds, sums up those values and produces an average. That average is then sent out to the web client, and you can see it there in the aggregate. And you'll notice that this Unix timestamp increments every time a new aggregate is received. Now, something you might also notice is these UUID values. So the UUID here is the node, the pod that we're connected to over WebSockets. The UUID down here is the node or the pod that is producing the aggregates. But what's interesting about this is they may or may not always be the same. As we can see, I refreshed here. I'm connected to this pod via WebSockets, but I'm getting aggregate data from this other pod because it's more regularly getting the lock to do the aggregation. So if we go and look in the logs at one of these pods, you'll see, once it catches up, that every time there's an aggregation event, the instance reports whether or not it's clustered. If it is clustered, it reports the number of nodes and their names that are in the participation of the cluster, and that it's firing off the periodic polar, whether or not it's obtained the distributed lock via the Vert.x clustering, retrieved data from the distributed shared data on the cluster. Then it formats the data and it clears the counters. And then it sends the aggregate data over the event bus in Vert.x, which then streams out to the browser over WebSockets. And this happens every 2 seconds. Now, every time I click or move my device, if I'm using the mobile, we should see data streaming into one of these pods. And we just got to find the right pod to see those logs. But what's beautiful about this is that it scales very, very simply. The MQTT server process is actually baked right into the Vert.x application. The WebSockets is baked right into the Vert.x application, and it's connected to the actor and event bus capability. So for example, if we were to look at the code for this, you'll see that it's made up of 5 relatively small Java classes. There is a main vertical, which handles starting up the application and reporting its readiness. So this application sets up a WebSocket handler, a web router. It can serve up my single page application, which handles the client side. That serves up some configuration. And then it deploys the other components of this application, the MQTT vertical and the aggregator vertical. The MQTT vertical starts up the MQTT service, the MQTT server, which is a component that is built right into the Vert.x ecosystem. And we've set it up to use WebSockets, and we've set it up to enable SSL or disable SSL by default because we're offloading the TLS termination to Kubernetes. And what you'll see down here is once we get the MQTT server up and running, we can set a listener for published messages on the particular topic that we want to be aware of. So the topic name that we're looking for is vibration data streaming in over MQTT. Every time we get vibration data, we add it to these distributed counters that are part of the Vert.x cluster. So we add to the X motion, add to the Y motion, and we increment the event counter so that we can build those averages. And finally, we have our aggregator vertical. The aggregator vertical basically fires a periodic timer every 2 seconds by default. You can see that we've got that defined as a static constant up there. So every 2 seconds, it calls try aggregate, checks to see if we're running in a clustered mode, and outputs whether or not we're in a clustered node. If it is a clustered mode, it will output a list of all the cluster members. It adds a little bit of a random delay so that I can get the aggregator to get locks on different pods on different times. So it initializes the shared data variables. It then stores the values from the shared data variables. Then it adds another short random delay to help me show off that the locks were actually working, because the locks were actually going too fast in my demo application. And so all of the verticals were successfully getting locks and sending aggregate data. Then it calculates how long it was before the lock was granted, and then it bills out the aggregate by calling this aggregate with the lock. So it retrieves the data from the shared data items, it formats the data, it sends it over the event bus, and then it zeroes out the values. Now the event bus is connected via this sock.js event bus bridge handler to the web application running inside of Vert.x. Which means that, for example, if I switch back over to my browser here and I open up the developer tools and I hit refresh, some of the last couple of connections that we'll see is, first, we see this MQTT, and we actually have a real connection to the MQTT service running inside of Vert.x. And every time I click, you'll see that it's sending data over here on every click via MQTT. Additionally, here's the WebSocket connection for the user interface. And we can see that every 2 seconds we get a new aggregate coming from the server. So we're using distributed processing inside of a clustered Vert.x application to collect, aggregate, and structure our data that we could then stream up to a head office or to the cloud for further processing, thus reducing bandwidth, thus reducing the amount of processing required at the cloud end, and also making this very, very scalable. So at this point, we could actually go back over here to look at our topology. We've got 5 pods now, but we could turn this around and use a horizontal pod autoscaler so that we could automatically scale it up or down based on CPU utilization. Now, I don't have a horizontal pod autoscaler defined in this particular environment, so I'm just using a Helm chart to change the number of replicas. But what you'll notice is that as I change this, that the application itself continues to function, even though the nodes have swapped out and changed. Even though we killed a couple of pods, the data is still streaming and it's still working as we would expect it to. That's a very effective solution for IoT. So, thank you for joining me on this journey. I look forward to talking to you in more depth and answer your questions, and enjoy the rest of the J4K conference.